بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. In this tutorial we'll talk about Verilog and Quartus. يعني we'll talk about Verilog modeling. Or sometimes we call it HDL modeling, Hardware Description Language modeling. What we mean by modeling? We mean we need to describe our circuit for the sake of simulation. And there are several programming languages used for this purpose. The most widely used languages are Verilog and VHDL. We will use Verilog on this course. We mean by that we start by designing by the design for our circuit. Then we describe our circuit using Verilog. So using a code to describe the circuit, then utilize this code to do simulation. The purpose of the simulation is to verify the correctness of the design. And before we implement the circuit, we first design it and then we make sure that our design is correct using the simulation. And to do that, we need to know two things. First, we need to know Verilog at the basic. Then to use Verilog, we need an IDE, interactive development environments. Like when you use Python, use, for example, PyCharm or use VS Code. Use VS Code to write Python, for example, and to run it. Same thing, we use an IDE to write Verilog, then we run it to simulate the circuit. There are several IDEs. One of the most very famous IDEs is the Quartus from Intel. Quartus. And there is also another IDE from Xilinx. It's called Vivado, but it's not free. For Quartus, there are several versions. There is the Pro version, and there is the Lite version, or they call it the Prime Lite version. Prime Lite version. So the Prime Lite version is free. At least for most of the versions. We will deal here with version 20.11, which we recommend that you download if you want to use Quartus. Other variants you will need some license for the simulators. You can use either 20.11 or lower. We recommend this version. And you are not required to use Quartus. You can use any other under IDE, and there are some online IDEs, but they are very simple. But the Quartus is very good, very easy to use. Although it is heavy, but still very easy to use. So we'll start by how to download the Quartus. Then we'll talk about Verilog using examples. Let us start talking about the Quartus first. Let's go to Google. If you go to Google search and you write Quartus, and you go to the first link, FPGA design software, click on it, Quartus from Intel, then go down, then go to ready to download and start designing, go to download. Now you see here the version. This is a Pro, we don't want a Pro, we want the Lite. Prime Lite. For the version we said use 20.11. Higher version will need some license, but this is free. Then you can start downloading. There are two ways to download. either download on one file, which is very heavy, which is 6.4 giga. If you want, you can do that. Otherwise, it's better to download individual files. You can download these two files only. Oh, sorry, these two files along with one of these files. So you need to download the simulator and the Quartus itself. Then you need to download one of these devices because this will be used to program the FPGA cards. You don't need to program FPGA cards. You will not do that here, but it's required at least to have one of these files. We recommend that you download the smaller one, which is this one, the max one, 811.4. So you'll download three files. One, two, then this one. And then you run only one file, which is the Quartus. Once you run this file, it will and it will and download also, it will install this one also, the simulator, and it will install the device. So you need only, you will download 1, 2, 3, but then you will install only one, which is this one. And this one will install everything. But all of them must be in the same directory, the three files. Once you download all of these files, then you will get the Quartus. Let us see the Quartus. If you go, this is the icon for the Quartus. Double click it. This will start the Quartus. Now you're ready to describe your design. Let us see what design we want to do here. Let us see examples. We saw this is introduction to Quartus and Verilog. We already downloaded the Quartus, which is the IDE. Now we'll talk about Verilog. But we said before you do any Verilog, you have to design a circuit first. And let us go to some of the circuits that we presented in chapter 4. Let us start with the half adder circuit. This is the half adder circuit. If you remember, the half adder circuit will add two inputs, X and Y, and it will generate sum and carry. When we design this circuit, we use the truth table, and from the truth table, we computed two functions, the S and the carry. And this is the drawing of both. This S is X, Y bar, and it ORed to X bar Y. And the carry is X and Y. This is the logic diagram for the design, and this is the Boolean functions. And you can write a module for the circuit like a function. And you can describe this circuit using Verilog, using something called module. A module is similar to a function. You need to define the inputs and the outputs, and then you need to find how the circuit is constructed. Okay, let us start with this module. Now we'll have two different ways to do that. This way we use the logic gates directly, and this way we use the Boolean functions. We call this structural design, we call this data path design, but both of them reflect our design. So it's okay to use this one or this one. This is similar, but let us see both. Okay, let us start with the simplest one, which is the one using the Boolean functions. This is the block diagram of our circuit. It has two inputs, X and Y, two outputs, S and C. We number them because we need to follow this numbering in writing the code. This is the order of the parameters. We'll start with X, then Y, then S, then C. How to write a module to describe the circuit? We say module, then we give it a name. We name this half adder. Then parentheses. Then we define the inputs, input X, comma, input Y, comma, output S, comma, output C. There's no comma here. Then we close the parentheses, then semicolon. Then at the end we say end module. Now in the middle here we describe the circuit using the logic gates or using the Boolean functions. We'll start with Boolean functions. To describe or to write a Boolean function, we start with a keyword assign. We say assign C equal X and Y. This is the symbol for and in Verilog. It means X and Y, then semicolon. This is the C. The S, assign S equal S and tilde is not. This is not Y. and this is the OR operation. This is not X and it to Y, then semicolon. We don't have parentheses here because we know the order of execution. The the AND comes before the OR, so the ANDs will be executed. First the NOT gets, then the two ANDs, then the OR operations. So we don't need to use parentheses here. Okay. Now let us see how to simulate this. Now we need to run this in Quartus and we give it some input and we see what is the output. If the output is correct, if output is similar to what we expect, that means the design is correct. Let us try this. Let us go to Quartus. Now to model any circuit, we start by creating a project. We go File, New Project, Next. Then we select the folder we want to put the project in. Let me use the not use, let me use the my documents. I use my documents. Although it's not recommended, sometimes you face problems when you use my documents, but I will do that here. Or let me use the C drive. Let me create a new folder. I'll call it EE360. So I'll use this folder for all my projects. Now inside this folder, I will name a folder for this project. I will name it adders or adder. Let me name it adder. What is the name of this project? I can use the same name. This is the name of the folder where we save our files. This is the name of the project. I will use the same name. I will keep this name as is. Then we'll talk about it later on. Then next. Does not exist the folder. Create it, yes. Then finish. We'll wait for the project to be created. So already created. You see here adder. Now I can bring the half adder module and test it, which is this one. Okay. We'll go back and come back to this later. So it's a file, new, Verilog HDL, then Control V. I will copy it from here, Control C and Control V. Let me copy this. Sorry. Control C, then Control V. And I need to save the file using this name. So I'll say Control C, save. I'll give it the same name, half adder. Or let me name it half adder 1 because we'll have two implementation for half adder. I'll name this half adder 1. Let me copy this name. Sorry. Control C, save, Control V, have other one, save. Now I'm ready now to simulate it, but before I do that, I need to change this name into the module that I want to simulate. I will say right click, settings, then in general, I'll put the name here. Control V, apply, okay. Now see, now we have other one, which is the top level design name. So this is the design we want to simulate. I will go here now, double click on analyze and synthesis. This will analyze the code and to generate the circuit. So double click. I'll wait till I get 0 errors. We will get some warning. We'll ignore them. Usually we get at least 1 or 2 warnings. Most likely they are normal warnings. Let us wait till this gets 100%. See, we have only 1 warning. Forget it. We have 0 errors. Now the tool understood the circuit, and we can see here here in tools, netlist viewer, RTL viewer. Sorry, netlist viewer, RTL viewer. See, this is the circuit. From the code, the tool could understand this circuit. This is the sum and this is the carry. Okay. Now we need to simulate. What do I mean by simulation? We mean that we need to give it some input and see the output. Okay. Once we are sure that the simulation is correct or the design is correct, then we can build the circuit. How to simulate it? We'll go to File, New, Verilog. Sorry, we'll go down here to University Program VWF. Double click. This is the simulator. We go to Edit, Insert, Node or Bus, Node Finder, List, and these are the inputs and the outputs of my circuit. I can click here. I will get all the variables. Say OK. OK. Now I have all these variables. Let me rearrange them. Let me pull this to up, then Y, then reorder them, then S and so on. So we have, now we need to define the X and Y and run the circuit and see what is the output. How to do that? We know that we have two inputs, X and Y, so we have 4 different combinations. I'll go to Edit, Set End Time. End time will be the number of cases. We have 4 cases. I'm using microsecond, okay? Then I'll go to Edit, Set Grid Size. Grid size will be 1 microsecond always. So now the screen is divided into 4 sections. Each section will represent 1 case. So we'll start with 2 zeros. This is the X. This is by default zeros. And then we have 2 ones. So we can click here and drag the mouse in this area. Sorry, this area. Oh, I'm sorry again. No, I want to just X. So this X now. I will click here now. 1 to make X1 in this interval and this interval. So we have 4 intervals. In this interval, X is 0, 0, then 1, 1. And you can see it here if you go to Edit, click here, Snap to Grid, and you can pull this bar. So in this interval, both X and Y are zeros. In this interval, also both are zeros because we don't change Y yet. In this interval, we have X equal to 1. And this interval also X equal to 1. For Y, we have 0, 1, 0, 1. So in this interval, we have Y equal to 1. I need to click here again. So now in this interval, sorry. Oh, again, I need to select only Y. So Y is 1, and in this interval also Y equal to 1. So now we have, if you check the 4 cases, let me drag this again. But let me also go and click here, Snap to Grid. So here we have X and Y both 0, 0. Then 0, 1, 1, 0, then 1, 1. So the last case is 1, 1. Now we are ready to run our simulation. But before we do that, just this for our version, which is, we said this is version 20.11. We need to do one extra step. We go to simulations, simulation settings. We go to 1, 2, 3, 4, the fifth line. Just remove this. Opt, remove this word only. And that's it. For some reason, there's I think a bug in this version. You need just to remove this, then save. Then now we are ready to simulate. I will click this button, which is Run Function Simulation. You will need to save this setup. I will say yes. I will keep the same name. Now it will run the circuit and give it these 4 different combination of outputs and generate outputs. Or inputs or generate outputs. Let us check now for the output. For the first interval, so not this interval, again I have to go to Edit, Snap to Grid. Let me now pull this bar now. 0 plus 0 is 0, sum 0 carry 0. 0 plus 1, sum 1 carry 0 is correct. 1 plus 0, sum 1 carry 0 correct. Last case, 1 plus 1, sum 0 carry 1, so design is correct. Now we are sure that our design is correct. We can now build the circuit. We are sure it is correct. Let me go see the other design or the other module. Okay. In that module, we use the Boolean function. Let us use the logic gates. So this is the logic diagram. Let us describe this diagram. For the inputs and the outputs and the header, they are the same because they are describing the same module. The only difference here, the description of the circuit. So here we can describe it using logic gates. We can use AND gates, OR gates. Okay, we'll start with this AND. We will say that we have an AND gate. Its name AND1. Its output is W1. We need to name this output. And its inputs are X and not Y. Not Y, we can use tilde Y. Semicolon. Then we have another AND gate. We say AND. Or before that, we do that. We did the not. Let me start with this one. But the order is not important. We'll say we'll have an AND gate. And we name it AND2. And the output of this gate is W2. The inputs is not X and Y. What is not X? Not X is coming from this inverter. So instead we use tilde, we use an inverter. We said not. We have a not gate called not1. The input X and the output is not X. And when we use the logic gates, we have to start with the output. So here we did not use tilde, we use a not gate instead. Okay. The order of this operation is not important. You can't put them in any order. This is a description only. Even you can start with the OR. Then we have OR gate that has an output is S. Inputs are W1 and W2. Finally, for the C, we have an AND gate. We named it AND3. And the output is C. The inputs are X and Y. Also, this will give us we can simulate this one. Will give me the same result. Let us see that. Let me copy this and create a new module. Control C. Go back to Quartus. We name this have either one. We name the second one have either two. We say new one. Verilog HDL. Control V. I will name it have either two. I will save it using this name, which is have either two. Control V. Then save. I will change also this top level design name settings. Instead of one, I will say two. Apply. Okay, now we have either two. Analyze and synthesis. Double click. We'll wait till we get 0 errors. You will have some warning. We ignore this warning. We have 0 errors. Now let us see the circuit. Let's viewer, RTL viewer. Same circuit. But here we built the circuit, or we described the circuit using the logic gates. There we describe the circuit using the Boolean functions. But we get the same circuit. Close this. Now we are ready to do the simulation. We'll say File, New. We'll go down to University Program BWF. It will open the simulator, Edit, Insert, Node or Bus, Node List, Node Finder, sorry, List. Let us put them in the order, in right order from the beginning. We start with X, then Y, then we need S, then we need C. Okay, okay. Same thing, now we'll have the same 4 cases. Let us divide the screen into 4 parts. Say edit, set end time. We'll make it 4 microseconds. Then edit, we set grid size, also 1 microsecond. Now we have 4 sections. We'll start with 2 zeros for the X and 2 ones. Sorry, this is the X again. So 2 0 2 ones. Then we have 1 0 1 for Y, then 0, then 1. And we are ready. Before we do that, we say go to simulation settings, 5th line, remove this not opt. This is just for version 20.11, which we recommend also because this is the latest version that you don't need a lesson for. Set. Now we are ready to simulate. This is the result. Go to edit, snap to grid. Now let us pull this bar. 0 plus 0, sum 0 carry 0. 0 plus 1, sum 1 carry 0. 1 plus 0, sum 1 carry 0. Then 1 plus 1, sum 0 carry 1. So design is correct. Let us close this. Now we are sure about the design of our half adder. Let us now design a full adder, but using half adder. And let us consider the design what we presented in the class. We said we can build a full adder using two half adders. If you want to add x plus y plus z and generate sum and carry, we can use a half adder to add x to y and generate sum 1 carry 1. Then a second half adder will take the sum from the first half adder along with the z and generate sum 2, generate the final sum, sorry, and carry 2. Then to generate the final carry, we ORed C1 to C2. And you can go back to chapter 4 and see this design. This is the design of a full adder using two half adders. Also, we need to verify this design through simulation by writing a Verilog module first and then simulate it. Same thing. Now to do that, I need to first define a module, call it full adder, define inputs and outputs. This is the order for the inputs. I'll start with x, then y, then z, then the output s and c. So we'll say input x, comma, input y, comma, input z, comma, output s, comma, output c. There is no comma at the end here. Then we close the parentheses, semicolon. Then end module. Okay. Now all interconnections or inside wires, we have to name them. Even we did this here, but we did not. I forgot to mention that. Here we name this wire W1, W2. Wire W1, wire W2. So we have to say wire W1, W2. So and inside wires we don't have to do it, but it's optional. But it's better. It's better to define them here as wire, unless they are multi-bits. These are single bits wire. It's better to define them as wire, and we will do this here also. So we have here interconnection here. This is called S1. This is a wire, and this is a second wire called C2, and this is C1. This is C2. These are not wires. These are outputs, and these are inputs. Okay. So intermediate wires, which we need to name them. Okay. We need to name them, but at least here, but it's option to declare them here. But we usually prefer to declare them. So we will declare the wire. Say we have wire S1, C1, C2, then semicolon. You can put it anywhere. It's better to start it at the beginning. Then we need to describe the circuit, starting from anywhere. I can start from this OR gate, or from this half adder, or from this half adder. I'll start from left to right. I'll start from this half adder. I will name it HA1. I will say I have half adder 1. Here I will use the module half adder 1. You remember, I have two modules for half adders. Half adder 1, half adder 2. Both are the same, but I will use both of them. I will use half adder 1 here, half adder 2 here. They are the same circuit, but we use different Verilog code to describe them. So we'll say I have a half adder 1 named HA1, and the order, when we built the half adder, we started with X and Y, then S and C. So the X is X, and the Y is Y, and the S is S1, and the C is C1, semicolon. Then I have half adder, but I use here half adder 2. I named it HA2. What is in X? S1. What is ny? Z. What is the sum? The sum is S. What is the carry? Is C2. Semicolon. Then I have an OR gate. Either I can use Boolean function using assign, or I can use OR gate operation. I use Boolean function. Here, assign C equals C1 or to C2. The order is not important because the OR operation is not as commutative. And you can say C or C1 or C2 or C2 or C1. Okay, so this is the description of this circuit. And usually, as we said, it's very important. We design, then we describe. And this description reflects our design. And let us verify our design through simulation. Let me copy this. Control C. We'll use the same project. Go File, New, Verilog HDL, Control V. I need to name the file using full adder name. Control C, save, Control V, save. Also, I need to change this name to full adder settings. Full adder, apply, okay. Now, double click in analysis and synthesis. We wait till we get 0 warnings. And 0 warnings. Now we are ready to submit. Before we do that, let us see the circuit. Netlist viewer, RTL viewer. See, we have two half adders and OR gate. If you click the half adder, you'll get the half adder we designed before. Okay, let's close this. Or let us go back here. If I click this one, the same thing, I have the same circuit. Then I need to close all of this. I'm ready now to simulate. Now we'll go to File, New, go down to University Program VWF. Now here we have 8 different cases because we're adding X and Y and Z. So we have 8 cases. We'll go to Edit, set end time. We'll make it 8 instead of 4. Then we change the grid size, define it as 1 microsecond. So we have 8 sections. Let us bring the variables, edit, insert, node or bus, node finder, list. Let me reorder them. I need to start with X plus Y plus Z, generate S, then carry. Okay. Let us start with X. X have 4 zeros and 4 ones. So we'll start here 4 ones. In this interval will be all ones. Then Y, we have 2 zeros, 2 ones. We have 2 ones here for the Y. Then 2 zeros and 2 ones. Then for the Z, we have 0, 1, 0. So we have 1 here. Also 1 here. Again, 1 here. And 1 here. Now we have all the 8 combinations. Let us check these combinations. Edit, snap to grid. Let us pull this bar. 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. Oh, sorry. This is, I think there's a mistake here. I don't know. Let us redefine this. We did not define it as 1. I think we clicked Z instead. Let us redefine this again. This should be 1. Sorry, not this one. Just the Z. Let me, I have to, again, sorry, to click snap to grid again. Then I'll do that here again. Oh, not this. Again. I need just X, just Z, sorry. Oh. Okay. I think I clicked Z instead of 1. Let me click on. Okay, so now it is all ones. Okay, we are ready now to simulate. But before we do that, let me go back to edit and click. Oh, no, it keeps not to grid. It's okay now. Uh, I can now simulate, but before we do that, we go to simulation settings. We need to remove this, knob opt, save. Now we can run the simulation. Now let us see the results. If you start with the last interval of 1 plus 1 plus 1, sum 1 carry 1. Let me go back to the beginning here. 0 plus 0 plus 0, sum 0 carry 0. 0 plus 0 plus 1, sum 1 carry 0. 0 plus 1 plus 0, sum 1 carry 0. 0 plus 1 plus 1, sum 0 carry 1. Then 1 plus 0 plus 0, sum 1 carry 0. 1 plus 0 plus 1, sum 0 carry 1. Finally, 1 plus 1 plus 0, sum 0 carry 1. So all the results are correct. So the design of the full adder is correct. Now let us go and see the 4-bit adder now. And we presented this design in class. So we designed the 4-bit adder using full adders. We have 4 full adders. We are adding A plus B. A plus B, all of them are 4 bits long. Add them together along with Cn, which is 1 bit long, and generate some 4 bit and see out 1 bit. So one full adder will add A0 and B0. Second full adder will add A1, B1, and here. Second full adder will add A1, B1 to generate some 1 and carry C2 and so on. يعني, first one we add A0 plus B0 along with the Cn and generate some 0 and carry C1. Then this one add A1 plus B1 plus C1 generate S1 and carry C2 and so on. The final one will add carry C2 plus B2 and A3, B3 and A3 will generate some 3 and C out. Okay, and this is the block diagram for the circuit. This is order start with A and B, then C and then some. Same thing, we'll define module, we'll name it for 4-bit adder, parenthesis. Then we define A, but A is 4 bits, is a vector. So we say A starts from 3 down to 0. That means from the most significant bit is A3 down to A0. So A3, A2, A1, A0. So from 3 down to 0. So this is from 3 down to 0. Same thing for B, 3 to 0B. Cn is single bit, input Cn. Output also for the S is 4 bits, starting from 3 down to 0. Then output C out, close the parentheses, semicolon, end module. Then we need to describe this diagram or to tell this story. Starting from anywhere, I can start from this full adder, or from this one, or from this one. But I will take it from right to left. So we'll have 4 full adder. Starting with the first full adder, we named it FA0. This will add X0 plus B0 plus Cn. So X0 plus B0 plus Cn will generate sum 0 and carry C1. Same thing for the second half adder, full adder, which is FA1 will add A1 plus B1 plus C1, generate S1 and C2. Then FA2 will add A2, B2 and C2. So A2, B2, C2, and it will generate sum 2 and carry 3. Sum 2 and carry 3. Finally, the last adder, which is FA3, also a full adder, named if A3 will add A3 plus B3 plus C3. A3 plus B3 plus C3. The sum is S3 and the carry is C out. Okay, now we are ready to simulate this design. Let us copy this module. Control C. File, new, Verilog HDL. Control V. Also, I'll copy the name here for bit adder. Control C. Save. Control V. Save. Same thing. Change this name. Settings. To 4-bit adder. Apply. Okay. Now we are ready to analyze the circuit. Double click here. We'll wait till we get 0 errors. Zero errors. Now we can do the simulation. New. Oh, before we do that, let's check the circuit. Tools. Net viewer tool, RTL viewer. See, we have 4 full adders. Each full adder, if you click on it, you get it is constructed using 2 half adders and an OR gate, and each half adder consists of several gates. Let's go to File, New. University of Grand PHFF. Now we have we have now so many cases. We have A is 4-bit, B is 4-bit, and Cn is 1-bit. So we have 9 bits, which is 512 cases. We will not present the 512 cases. And if you want to do that, there are ways you can use loops, but we'll talk about this in another session. But let us present at least 3 cases. Go to Edit, Insert, Node or Bus, Node Finder, List. Here now you see A as a group bits or as a single bits. I need A as a group. I need to add A to B and then to Cn. And this will generate sum and then C out. So now ready now to, but say we'll use 3 cases, go to Edit again, then set in time, we'll make it 3 microseconds, and then we'll set the grid size to 1 microsecond. Use microsecond. So we have 3 sections. Now we could undefine the input as either binary or decimal. Make it decimal. Let me define A. Can use binary or decimal. Let me use decimal. I'll set unsigned. Let me make it 15. This is the maximum possible value. I'll do the same thing for B. Also make it 15. I'm sorry, I have a problem with the mouse, but let me check the mouse. Unsigned decimal. Also will make it 15. Same thing for now. This is A and B. Let me Cn also make it 1. Cn is single bit, make it 1 here. For the second case, I'll make, for example, A. Let me make it maybe 4. B maybe let me make it maybe 11 or 10, make it 10. Now here for A, let me make it 12. Maybe B, you make it maybe 5. Okay. Now we go to simulation settings, go to fifth line, then save. Then we are ready to simulate. Click here. Yes. Save. It will run the simulation. Now see now the output is in binary format. Let me change it. I'll change the output into say radix. I'll say unsigned, for example. Now 15 plus 15 plus 1, it should be 31. 15 plus 31, but now the output is split into two portions, the S and the C out. Let me see the output in binary. Binary. So now we have the S is 4 ones. So the S is 4 ones. And the C out is 4 ones. So this is the complete output, which is 31. This is 31, actually. Because a part of the output in S and 1 bit in C out. For this case, we don't need the C out because 10 plus 4 is 14. 14 is already saved in S. It's 14. 14 is saved, and the C out is 0. So it's clear C out is 0. Same thing here. Now here we have 12 plus 5, which is 17. So we have S is 1, 0, 0, 0, and the C out is 1. So this is 16 because 1, 2, 4, 1, 2, 4, 8, 16. And 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, which is 16, plus 1, which is 17. So the output is S and C out, 5 bits. If you want to see the output in a single variable, we can do that. We can change the module to combine the C out with the S, and we'll see that now. Let us see that. But it's clear, at least for these three examples, the simulation is correct. Let us change the module a little bit to combine the outputs. So let us do that here. So I will remove the C out. I don't want to C out. I will keep the CN, no problem. But I will change here. I will make S is 5 bits instead. So the C out will be saved in the 5th bit, the 4th bit, which is S4. So now the sum and C out, all of them combine into S, into a single variable S. Now here we can see the result in decimal directly. Let us save this module. Let us do analysis again. Now the design chain, now we need to reanalyze the circuit and redo the simulation, rebuild the simulation inputs and run the simulation again. Okay. File, new. Now let us do just two examples. Edit. Uh, sorry. Set end time. We'll make it just two. And then the end time will be 1 microsecond. Oh, sorry, the grid size. The grid size. Grid size is 1 microsecond. Now we have to two sections, two intervals, edit, insert, node or bus, node finder, list. We need to add A to B. Also we have Cn plus Cn. Now, yes, we don't have Cr, we have only S. Okay, okay. Now let us do the same example. Make X and A and B both equal 15. Unsigned. You can make it binary if you want to make it binary. You can make it binary. Say for once. Okay. Then you can change it into decimal if you want. We'll do that later, but let me define this. Let me to use a different example here. Let me define it in a decimal unsigned. Let me make this 5. And this is maybe 12. Okay. And let me show the output in decimal also. Make it unsigned. Also, let me change the Cn here at least here. Make it 1. From here or from here. So we'll have 15 plus 15 plus 1 should be 32, and we have 5 plus 12 plus 0, which should be 17. Simulation settings. Remove this line, this knob opt. Then save. Then we run the simulation. Yes. Save. See, 15 plus 15 plus 1 is 31, correct? And 5 plus 12 plus 0 is 17, so it's correct. So the designs are correct. This verifies that our design for the 4-bit adder is correct, so we can build the circuit. Usually when we design, we start from top to down. We call it top-down design. So when we design 4-bit adder, we start with this block diagram. For 4-bit adder consists of 4 full adder. Then after that, we design the full adder, either using Boolean function or using half adders. If I will design it using half adder, so I need to design the half adder. If I will design it using just Boolean function, I don't need to use the half adders. And this is the end of the first session in this series. And this is an introduction to Quartus and Verilog. We will have one more session where we'll have a complete design problem similar to the problem assigned to you. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك